Well, thank you for your interest in Apse and RNA for RNAi in agriculture. There's a little bit of overlap. I should have coordinated with Nitsan, but that's okay. So what if I told you that there was an environmentally benign and non-GMO way to selectively control harmful insects in the presence of beneficial insects that are not harmed? Or, as Nitsan said, alter insects to overcome pesticide resistance, or alter weeds that have become resistant to herbicides to make them susceptible again, or kind of the holy grail, altering crops in the field to make those crops do things that you want them to do. So a good example might be drought resistance, only when there's a drought. We're in the process of doing that, and we want to do it with a cost of RNA that's about $2 a gram. Mind you, the use rates are thought to be in the 1 to 5 gram per acre range. That's what we're all about. We've got a little bit simpler view of RNAi than Nitsan had. You know, you all know what DNA is, you know what proteins are. Well, RNA is just a template between the two, and RNAi destroys that template. And by destroying the template, the protein's not produced, and that's how it exerts its effect. So what are we all about? Well, there's some impediments to this technology. One of them is high cost of RNA. RNA is really hard to produce, and it's even more hard to produce in a very pure form. And it's also a very fragile molecule, so it tends to break down on the leaf surface or on in the insect gut. And we have technologies to address both of those. So what does it look like? So we convince a microbe to produce the RNA that we're interested in, and we give that RNA an address. And the address is to a little protein house that we also produce in the same microbe. And we put the RNA in the little protein house, and that makes it easy to separate out, as you can see here. And we separate it out, and once you separate the little protein houses out, you can do a couple things with them. You can break them down, get the RNA out, formulate the RNA, spray it, and get your effect. Or if you have issues like the stability that I mentioned earlier, well, just leave it in the little protein house, formulate that, and spray it. So it's fairly simple technology to talk about. It's a little bit more difficult to do. So what are the markets? Well, the markets basically are very similar to the normal crop protection markets that we're all accustomed to, and the seed markets. And just about anything that you see today done in either one of those markets, whether it's crop protection or seed, you can do with RNAi, and it's kind of a non-GMO approach to doing these things. So what's the competition? Well, there are about 4 ways to make RNA. One's a chemical process. It's fairly expensive even if you have automated synthesis. And if you have automated synthesis, your intermediates still eat you up. So the cost is very high, and you're limited to fairly short RNAs. There's a process called in vitro transcription. It's kind of a test tube process that can be scaled up to kilogram levels, but it's costly and very difficult to scale up to ton quantities. And then there's a fermentation process that you can use to make a lot of RNA, but it's very dirty RNA. It's got a lot of junk in it. It's very difficult to clean up, and thus it's costly to clean up. And then you've got the Apse process, which is low cost, high purity, and we've got 6 patents filed in this area. So what's the business model that we have? So basically, our business model is to license the production technology on a per sequence basis with an upfront payment and downstream royalties. But in order to get to that, you know, we work with our strategic partners doing research initially, development programs, as well as scaling up. And then what are our targets to get to that $2 a gram? We need to make 200 milligrams of the RNA per liter of fermentation. We're at 50 milligrams per liter of our fermentation broth now. We started at 1, so we're pretty confident we're going to get there. And on purity, We are at 50 to 80% purity of the RNA. Any of you who've done regulatory work know that the agencies usually like to have a pretty clear idea of what you're spraying. And we think that we're going to be above 90% in the end. Now, who's doing this? I've got a background at Monsanto, 30 years or so, and other companies, both in P&L and technology. Juan here has a background at Shell and Monsanto in chemical engineering, and our molecular biologist is from Novus. He's got a great background in molecular biology and fermentation. We've got advisors from WashU, St. Louis U, and a production advisor from Novus. So what are we looking for? Well, basically we're looking for resources to accelerate development, and that includes strategic partnerships to identify market opportunities, co-develop solutions, and commercialize applications. From a technology standpoint, we want to get away from sequential. We're a very small company. We do sequential research. We want to do parallel research to speed this thing up. We've got a $2 million round, and we've done about 400,000 of it so far. So that's what we do. We're excited about the technology, and we think there's great future in it. Thank you.
Questions? Take a question or two. Jim, anything? Budzinski.
So, John, how comfortable do you feel about moving from the next 4 notches in terms of the cost?
Of yield? Yeah, so we were happy at about 20 milligrams per liter of fermentation, and one of our board members said, hey, you know, I'd like to see something a little bit better than that. And we did it. I mean, it wasn't that tough for us to do. My focus, I think we're going to get a great kick when we shift towards fermentation, but we're not going to get much intellectual property doing a lot of fermentation work. So I want to fix the molecular biology first and get that straight, which we still have some ways to go on that, and then we'll shift to fermentation, and I'm confident we're going to get there. Thank you.
Questions? Thank you very much, John.
Yeah.
Appreciate it.